January 14, 2005. Inside a mission control room in Germany, about 260 engineers from 19 countries sat together, their eyes fixed on the monitors. A deep silence filled the room, the kind that exists only when your life's work depends on a machine that is 1.2 billion kilometers away. A machine named Huygens. At that moment, that machine could either be alive or lost forever. No one knew. For the previous 4 hours, the room had remained completely silent. No coffee, no conversations, no jokes. Just an unmoving signal on the screen. During those 4 hours, Huygens was carrying out something that had never happened before in human history. A probe had entered the atmosphere of the most mysterious moon in our solar system. Traveling at 6 kilometers per second, it was descending into a world where scientists had imagined every possible outcome. It might sink into a sea of methane. It might crash into an icy mountain and shatter. It might become trapped in a field of thick hydrocarbons. It might even break apart during landing. But none of those possibilities were the greatest concern. The real fear was something no one in that room said out loud. 5 years earlier, during this very mission, a mistake had been discovered that could have ruined the entire project. A mistake that a junior engineer had found during a routine test. A mistake that threatened a mission worth $3.4 billion. The engineers believed they had corrected it, but the solution had never been fully tested in flight. So now, whether Huygens had safely reached the surface, 1.2 billion kilometers away, would be revealed in only a few more minutes. Then, a single beep appeared on the screen. One sharp tone, then silence. A moment later, another beep followed, and then a steady signal that slowly transformed into a stream of data. Inside Mission Control, one scientist accidentally dropped the coffee cup from his hand. Around him, everyone rose from their seats. Some began clapping. Some began crying. Others simply embraced the person standing beside them. Far away, on a frozen alien world, a machine built by human hands was alive, and it was sending information back across the vastness of space. But the real story was only beginning. The images that Huygens transmitted during the next 90 minutes forced humanity to rethink one of its most basic assumptions. Perhaps Earth is not the only world in the solar system with familiar processes. Perhaps the ingredients for life are not unique to our planet. Perhaps Earth has a distant twin, a frozen, alien, hidden twin. A world where so much seems familiar, yet everything is made from different materials. A place with rivers, lakes, oceans, rainfall, and winds. But instead of water, those rivers and lakes are filled with liquid hydrocarbons. This is the story of that remarkable twin, that frozen second Earth, called Titan, Saturn's largest moon, a world where humanity explored the outer solar system in an entirely new way, a place where we discovered an atmosphere that may closely resemble Earth's atmosphere from 4 billion years ago. And today, NASA is preparing to send a drone there, one that may one day search for signs of life, or perhaps the very first chemical steps that eventually lead to life itself. Before we continue that story, it helps to understand the remarkable journey of the probe that reached this frozen world, and the mission that almost failed long before most people had ever heard its name. The year was 1997. It was an October morning at Cape Canaveral, Florida. A Titan IVB rocket stood waiting on its launch pad. At the top of that rocket rested a spacecraft weighing 5,650 kilograms, the heaviest payload ever launched on an interplanetary mission at that time. The spacecraft was called Cassini-Huygens. It consisted of 2 parts. Cassini was a NASA-built orbiter that would spend years circling Saturn, while Huygens was a lander built by the European Space Agency. It would travel alongside Cassini for 7 years before separating and beginning its descent through Titan's atmosphere. Reaching Saturn was far from simple. Cassini-Huygens was so massive that no available rocket could send it directly there. Instead, the mission relied on a clever technique known as gravity assists. Cassini flew past Venus twice, then returned for a close pass by Earth, and later swung past Jupiter. With each encounter, the gravity of the planet increased the spacecraft's speed, almost as though each world gently tossed it forward like a giant slingshot. During this 7-year journey, Cassini traveled approximately 3.5 billion kilometers, huygens the Huygens probe remained completely dormant. It would not awaken until the final 22 days before its descent. Yet hidden within that long journey was a problem serious enough to threaten the entire mission. In the year 2000, after Cassini had already traveled about 500 million kilometers toward Saturn, a junior engineer decided to satisfy a simple curiosity. He transmitted a simulated signal from Huygens' engineering model on Earth toward Cassini, simply to confirm that the receiver was functioning properly. He expected Cassini to relay the signal back exactly as designed. Instead, the response was complete gibberish. Nothing but random noise. The engineer stared at his monitor for a moment, then immediately called his supervisor. Soon, the entire team was involved, and over the following weeks, they uncovered something astonishing. Cassini's receiver could not properly handle the Doppler shift. The Doppler shift is something we experience in everyday life. When something moves toward you, its sound seems higher in pitch. As it moves away, the sound becomes lower. It is the familiar effect you hear when an ambulance passes by. The same principle applies not only to sound, but also to radio waves. As Huygens descended through Titan's atmosphere, its speed relative to Cassini would constantly change. That meant the frequency of its radio signal would shift continuously. Unfortunately, Cassini's receiver had not been designed to compensate for those changing frequencies. When the most important moment of the mission arrived, Huygens could transmit perfectly, yet Cassini would interpret much of that information as meaningless noise. A mission worth $3.4 billion suddenly stood on the edge of failure. The most frightening part was that Cassini's receiver settings were already locked in space. Solving the problem required what would normally be considered a hardware-level fix. But the hardware was now hundreds of millions of kilometers away and traveling even farther every second. Even so, the engineers refused to give up. They created what is still considered one of the most brilliant solutions in the history of interplanetary exploration. If the receiver could not compensate for the Doppler shift, then they would reduce the Doppler shift itself. Instead of changing the receiver, they would completely redesign Cassini's flight path so that the relative speed between Cassini and Huygens during the descent would be much lower. Over the next 4 years, the engineering teams rewrote the mission timeline and trajectory almost from the ground up. The original plan, in which Cassini would release Huygens during its very first flyby of Titan, was abandoned. A new strategy took its place. Cassini would first make several flybys of Titan to reduce its relative speed. Only then would it release Huygens from a carefully calculated angle. They also changed the way Huygens would wake up. Unlike many other spacecraft, it would activate earlier than originally planned, so its internal temperature would be slightly higher and its radio signals would remain a little more stable. These changes came at a significant cost. Cassini would consume more of its precious fuel, and Huygens would use more of its limited battery power. But there was no alternative. Without those sacrifices, the mission would almost certainly have failed. Then came December 25, 2004. On Christmas Day, after traveling together for 7 years, Cassini finally released Huygens. A small spring mechanism gently pushed the probe away at a speed of 0.35 meters per second while giving it a slow spin of 0.35 revolutions per minute. That slow rotation was carefully designed to keep Huygens stable as it entered Titan's atmosphere. Now Huygens began a silent 22-day journey through space. During those 22 days, it remained completely dormant. Only 3 independent backup timers continued running. Their single responsibility was to wake the spacecraft exactly 4 hours and 23 minutes before it reached Titan's atmosphere. Those 22 days brought a different kind of tension to mission control. Huygens was now completely beyond their control. If it failed to wake up, the mission would end. If one of the timers failed, the mission would be over. If any component had been damaged during the 7-year journey in a way that could never be tested from Earth, The mission would fail without warning. Then, on January 14, 2005, at 9:05 in the morning, Huygens woke up. Its instruments powered on. Its sensors became active. Its radio transmitter began broadcasting. 4 minutes later, it deployed its first parachute, measuring 8.5 meters across. At that exact moment, however, another failure was unfolding, and no one knew it. Huygens was transmitting its data through two independent communication channels, known as Channel A and Channel B. Each channel existed to provide redundancy. If one failed, the other would preserve the mission. But hidden within Cassini's software was a missing programming command. The receiver for Channel A had never been switched on. Throughout the entire 90-minute descent, Huygens faithfully transmitted its priceless scientific measurements and its historic photographs over both channels. Cassini, however, was listening only to Channel B. Everything sent through Channel A disappeared forever. Even today, more than 20 years later, those lost moments have never been recovered. Around 350 images were transmitted but never recorded, all because of a single programming command. One missing line of code permanently erased half the photographs from a mission that cost $3.4 billion. Even so, the images that arrived through Channel B were enough to transform humanity's understanding of Titan. As Huygens descended through the thick orange haze, its camera gradually revealed the surface below. What appeared was something almost no one had expected: a dark valley surrounded by brighter highlands. Running through that valley was an intricate network of branching channels. Those channels looked remarkably familiar. They resembled river systems on Earth. Such patterns are created only by flowing liquid. That meant liquid had once moved across the surface. That meant rivers existed there. That meant rainfall was part of this distant world story. Yet this was not Earth. This was Titan, Saturn's frozen moon, where the surface temperature is about -179 degrees Celsius. Water could not remain liquid under those conditions. So what was flowing across the landscape? The answer was both strange and extraordinary. The rivers and lakes were made of liquid methane and liquid ethane, the same gas we know on Earth as natural gas, the fuel used for cooking in many homes. But in Titan's extreme cold, that gas becomes a liquid. It forms clouds, falls as rain, flows across the surface in rivers, gathers in lakes, and eventually fills vast seas. It is a complete hydrological cycle, remarkably similar to Earth's, except that instead of water, the entire system is powered by liquid methane and ethane. This was the first time humanity had ever observed stable liquid on the surface of another world. As Huygens continued its descent, it drifted toward one of the dry riverbeds within that remarkable drainage system. When it finally touched the surface, it left a dent about 12 centimeters deep. Then it bounced gently, slid another 30 to 40 centimeters, wobbled slightly, and finally came to rest. A machine built by human hands, resting quietly on an alien shoreline 1.2 billion kilometers from Earth. What its camera revealed next remains one of the most unforgettable images ever returned from another world. The ground had a deep brown-orange color. Scattered across the landscape were rounded stones, much like those found along riverbeds on Earth. They were smooth and polished, their shapes clearly altered by the movement of flowing liquid over long periods of time. But these stones were not made of rock. They were made of water ice. On Titan, temperatures are so unimaginably cold that water freezes into something as hard and solid as stone. Around those icy rocks lay smaller pebbles resting on a soft, muddy-looking surface made of frozen hydrocarbons. The upper layer appeared dry and slightly crusty, while beneath it the material was softer, almost like damp snow hidden beneath a thin frozen shell. It looked remarkably like a beach, a frozen, alien beach, where waves may once have washed ashore before the shoreline slowly dried. Just as beaches on Earth change with the passing of seasons, this distant shoreline seemed to tell the story of a changing world. When the camera turned upward, it found the sun hanging in Titan's sky. But from that extraordinary distance, The sun appeared only about 1/10 its familiar size. Its light was so faint that even midday on Titan resembled the gentle glow of twilight on Earth. A permanent orange-brown twilight stretched across the landscape, never becoming truly bright. Then something happened that surprised everyone. A tiny droplet appeared on the camera lens. It was methane. Liquid methane near the surface had begun evaporating because of the warmth generated by one of Huygens' instruments, creating a small amount of condensation on the camera. For the first time, scientists watched subtle signs of weather unfolding on the surface of another distant moon. The atmosphere was active. The wind was moving. Temperatures were changing. Titan was frozen, but it was far from lifeless. There was another surprise waiting. Huygens had been designed to operate on Titan's surface for only 30 minutes. Its battery capacity allowed for just half an hour of work. After a 7-year journey through space, 22 days of silent drifting, and a challenging 2.5-hour descent, those 30 minutes represented its final opportunity to share everything it had discovered. But Huygens refused to stop. 30 minutes passed, then 40, then 50. The little spacecraft continued working for 72 minutes, more than twice its expected lifetime. When its signal finally faded away, many engineers inside Mission Control found themselves overcome with emotion. This small, determined spacecraft had accomplished far more than anyone had expected. Those additional 42 minutes of operation provided some of the most valuable scientific information from the entire mission. Even then, one mystery remained. Huygens had landed inside what clearly looked like a riverbed. But the riverbed was completely dry. So where had all the methane gone? Over the next 13 years, Cassini gradually uncovered the answer during its 127 close flybys of Titan. Titan has a hydrological cycle remarkably similar to Earth's, yet it behaves in a very different way. On Earth, sunlight is strong enough to drive rapid evaporation almost everywhere. Water continually evaporates, forms clouds, and returns as frequent rainfall. Titan receives far less energy from the distant sun. Evaporation happens very slowly. As liquid methane gradually evaporates, it forms extremely dense clouds, capable of storing enormous amounts of vapor for very long periods. As a result, Titan can experience droughts that last for centuries. Then, eventually, those clouds become so saturated that they can no longer hold their contents. When that moment arrives, enormous methane rainstorms unleash sudden floods that reshape the landscape. Dry river channels fill once again, valleys are carved by flowing liquid, and lakes return to places that had remained empty for generations. Eventually, the floods subside, the rivers dry once more, and another centuries-long drought quietly begins. Huygens simply happened to arrive during one of those long dry periods. As Cassini continued exploring Titan through the years, it witnessed scenes that were even more astonishing. Near Titan's polar region, it discovered a large methane lake called Ontario Lacus, named after Lake Ontario in North America because the two shorelines share a striking resemblance. Covering roughly 15,000 square kilometers, with depths ranging from about 40 centimeters to 3 meters, it is an incredibly calm body of liquid. The tallest waves measured only about 3 millimeters. That was unexpected, because Titan's weaker gravity should allow methane waves to become much larger than waves on Earth. Yet they remain surprisingly small. Even today, scientists are still investigating why, and Ontario Lacus was only the beginning. Near Titan's North Pole, Cassini discovered something far larger, an immense sea known as Kraken Mare. Covering about 400,000 square kilometers, slightly smaller than Earth's Black Sea, Kraken Mare is an enormous ocean of liquid methane and ethane. It is so vast that Saturn's gravitational pull creates real tides across its surface. The liquid rises and falls by as much as 1 meter, just as Earth's oceans respond to the gravity of our moon. Here was a moon orbiting Saturn, wrapped in a thick atmosphere, holding seas of liquid hydrocarbons so large that tides rolled across them. It was not Earth. Yet, in many remarkable ways, it felt like another version of Earth, shaped by entirely different chemistry. Then, the story became even stranger. Titan does not only have rivers, lakes, and seas. It also appears to have volcanoes, but these are unlike any volcanoes on Earth. Titan's crust is made primarily of ice rather than rock. Instead of erupting molten rock, these volcanoes may release slushy mixtures of water and other compounds. They are known as cryovolcanoes or ice volcanoes. That naturally raises an intriguing question. How can water remain liquid in a place where the surface temperature is about -179 degrees Celsius? The answer begins with a remarkable substance: ammonia. In nature, ammonia acts as a powerful antifreeze. Ammonia was abundant during the early formation of the solar system, and deep beneath Titan's frozen surface, a mixture of water and ammonia can remain liquid even under extraordinarily cold conditions. As Cassini continued studying Titan, its gravity measurements revealed another remarkable discovery. Hidden beneath the surface lies a vast subsurface ocean. This is not a small underground reservoir. It is a global ocean made of liquid water mixed with ammonia, surrounding the entire Moon at depths of roughly 55 to 80 kilometers below the icy crust. Titan is, in many ways, a layered world. At the top lies a hard shell of water ice. Beneath that is a partially frozen layer of slushy ice that may occasionally reach the surface through cryovolcanoes. Farther down rests a thick global ocean of liquid water and ammonia, covering the rocky interior of the Moon. And this is where Titan becomes truly fascinating. There are 3 ingredients found together on Titan that, as far as we know, exist in the same combination only on Earth. The first is hydrocarbons. These carbon and hydrogen molecules are considered some of the fundamental building blocks needed for life, and Titan's surface contains them in extraordinary abundance. The second is water. Hidden beneath the ice is an immense ocean, believed to contain more liquid water than all of Earth's oceans combined. The third ingredient is energy. Occasionally, warmer material from below may reach the surface through cryovolcanic activity. Whenever water and hydrocarbons come into contact, they create chemical conditions that resemble those believed to have existed on Earth about 4 billion years ago. In other words, some of the same environmental ingredients that may have helped life begin on Earth appear to exist on Titan as well. In 2024, another discovery made this picture even more intriguing. Researchers found evidence that methane gas is trapped within Titan's icy crust in deposits reaching nearly 6 miles in thickness. That methane acts like insulation. It slows the escape of heat from the ocean below, suggesting that Titan's hidden ocean may be warmer and potentially more favorable for complex chemistry than scientists had previously imagined. Then, in July 2025, NASA published laboratory research that captured the attention of the astrobiology community. The experiments demonstrated that conditions similar to those found in Titan's lakes can naturally produce structures known as vesicles. A vesicle is a tiny compartment enclosed by a membrane, almost like a microscopic bubble. On Earth, structures resembling vesicles are believed to have played an important role during the earliest stages in the origin of life. Now, laboratory experiments suggest that Titan's hydrocarbon-rich environment can naturally create similar structures. This is not simply a theoretical idea. Scientists have successfully reproduced the process under laboratory conditions. Then came another important discovery in October 2025. Researchers found that hydrogen cyanide, an important chemical involved in many prebiotic reactions, can dissolve into hydrocarbons under Titan-like conditions. For many years, scientists believed this should not happen because hydrogen cyanide is a polar molecule, while hydrocarbons are nonpolar. Yet, under Titan's unique environmental conditions, the chemistry behaved differently than expected. That discovery suggests Titan's lakes may provide an even more favorable setting for the kinds of chemical reactions associated with the earliest stages of life. Taken together, these discoveries have made Titan one of the most exciting destinations in the search for life's origins. That is one reason NASA has committed to one of the most ambitious planetary exploration missions ever attempted. The mission is called Dragonfly. Dragonfly is not a rover. It is not a traditional lander. It is a nuclear-powered flying drone equipped with 8 rotors, designed to travel through Titan's thick atmosphere. About the size of a small car, Dragonfly will be powered by a radioisotope thermoelectric generator, often called an RTG, which produces electricity from the natural heat released by plutonium. It will become the first fully controlled powered aircraft to carry out an extended scientific mission on another world beyond Earth. The Mars helicopter Ingenuity demonstrated that powered flight was possible, but each flight lasted only a few minutes. Dragonfly is designed for something entirely different. Its mission centers on flight itself. Over approximately 32 months, it is expected to travel nearly 1,174 kilometers, covering more ground than the combined driving distance of every NASA rover that has explored the Moon and Mars. The planned launch is scheduled for July 2028, with arrival at Titan expected in 2034. Its destination is Selk Crater, a location where scientists believe an ancient impact mixed water with methane and other hydrocarbons. The tremendous heat generated by that impact may have created pools of liquid water that remained warm for thousands of years. Those conditions may have provided an ideal environment for prebiotic chemistry. Dragonfly will investigate those ancient deposits directly. It will collect samples, analyze their chemistry, and search for evidence that the chemical processes occurring there represent the stage immediately before life begins. Then, in March 2026, the team at the Johns Hopkins Applied Physics Laboratory announced another important milestone. Dragonfly had entered its integration phase. Its rotors had already completed testing. Its parachute system had successfully undergone drop tests in the Arizona desert. Its laser instruments, designed to study Titan's sand-like surface, had also completed testing. The mission was no longer just a collection of plans and computer models. The hardware had become real. Many of the scientists building Dragonfly today may be retired by the time it finally arrives at Titan in 2034. Yet they understand that the spacecraft they are creating may help answer one of humanity's oldest and most profound questions. Are we alone? And with that question, our story returns to where it began. January 14th, 2005. A quiet mission control room. Engineers representing 19 different countries. A small spacecraft resting on an alien shoreline 1.2 billion kilometers from home. For 72 unforgettable minutes, it quietly shared the story of another world. Then, the signal faded away. Huygens became silent. It still rests there today. 21 years have passed. Its battery was exhausted long ago. Its camera lens was gradually covered by frozen methane deposits. Its instruments slowly surrendered to the relentless cold. A modest European spacecraft, the first machine ever to touch the surface of the outer solar system, now remains quiet, alone, and frozen beneath Titan's hazy sky. A forgotten explorer that accomplished the most distant landing in human history still rests exactly where it came to a stop in 2005. And in 2034, on that same distant moon, perhaps only a few kilometers away, Dragonfly will take flight. It will represent a new generation of exploration, continuing the journey that Huygens began so many years earlier. Perhaps somewhere beside one of Titan's methane lakes, or within the ancient sediments of Selk Crater, Dragonfly may discover something capable of changing our understanding forever. Perhaps it will detect a molecule showing unexpected behavior. Perhaps it will observe a vesicle capable of reproducing itself. Perhaps it will find a pattern that is no longer random, but something that hints at life. Where did life on Earth truly begin? Perhaps the answer is not found only on Earth. Perhaps part of that answer has been waiting quietly within Titan's frozen methane lakes, on a distant moon orbiting Saturn, nearly 1.2 billion kilometers away. A world that resembles our own in extraordinary ways, yet is built from entirely different materials. When Huygens gently touched Titan's surface on January 14, 2005, the small 12-centimeter impression it left behind did far more than disturb the frozen ground. It awakened one of the greatest questions humanity has ever asked. Is life a story unique to Earth, Or has Titan been writing a story of its own, slowly and patiently, across billions of kilometers, through frozen lakes, gentle methane rain, and hidden oceans, simply waiting for someone to arrive and read its pages? The countdown toward July 2028 has already begun. And somewhere beyond the familiar planets, Titan continues to wait in silence. Its winds still move through the orange haze. Its methane rains still fall. Its hidden ocean still rests beneath the frozen crust, patiently keeping its secrets until the next visitor arrives.